particular project that SMV has been working on over the last couple of months. Super excited to sort of share that update on what's been going on with all of you. I think sort of there are certain projects in SMV, well, all of the projects in SMV. There are certain projects in college where you can sort of see the impact that they have. They do a lot. They do a big part in moving our entire organization forward, bringing us closer to building the world's most efficient car and competing more effectively at competition. And the dyno that we're going to talk about is a great example of that. So it's a pleasure to be able to work on this project and combine that with the team that's as fantastic as the dyno team is, and it's a dream. So yeah, that's all I wanted to say. With that, I'll turn it over to Juan. Juan, you want to share your screen, and we can get started. I'd sort of ask. I guess I'll challenge all of you to come up with some tough questions. It's also still a work in progress. So any tough questions or suggestions that any of you have will definitely be incorporated. So please be vocal. You can drop them in the chat or just unmute and say them at any time.
All right, can you see that?
Yeah.
Let me do it like this, actually. Okay. All right. So the first question you may be asking is, we're talking about that dynamometer. I'll get into what that is. But first, why are we making a dynamometer? So there's three places where I really see the possibility of making our car more efficient. At the very top is the shell, which we make out of carbon fiber. It doesn't look like that, but I know you all have seen the car. And the idea is there's aerodynamics, making it really smooth in order to make air breeze through, have less drag, and reduce some power consumption that way, make it more efficient. The other is the engine. It's the source of basically everything that pushes the car forward, right? Be it the engine or the motor, depending on which car we're talking about. And that's, of course, one place where you can have a big impact as well. How efficient your motor is, how efficient you're going to go in the race. And lastly, the chassis, which is strength and support, is sort of the weight. If you reduce the weight of the car, it's basically going to be easier to push it forward. So out of all these three, we've sort of meddled with all of them. This specific project tackles one of the biggest, I think, which is the engine power and finding that efficient point. And what is a dynamometer? Basically, a dynamometer is something that allows you to test your engine or your motor. As you can see, we have down here sort of rendering of the engine, where we can connect this right here to the axle and we'd spin a flywheel to pretend as if we were moving the car. With this, we can make some pretty accurate measurements of basically the energy that we're using, and that way we can see our efficiency overall. So we've had a great team working on this, and I think the most amazing thing is that we did it all through the summer, basically fully virtual, and everyone is here to tell you a little bit about the things that they did, and they'll tell you specifically what they worked on. So to move straight on, I'll pass it on to Mirayna.
Awesome. So I'm just going to talk about our RagTag team. Right before we left in spring quarter, we all got together at BCAF, and it was just a mix of special projects and structures, and Abs ended up joining, so I threw an admin. But we just kind of dove in and tried to put this thing together, put our heads together. We ended up using Messenger for most of our contact and then Zoomed every week. Next one.
So yeah, this is a video Miranda made. It's kind of good.
Oh gosh.
Dude, I'm
share sound as well.
Let me put that. My apologies.
Didn't know there was going to be a video. What?
Anyway, that was the awesome team that we had meeting together pretty much every Thursday to put together this project for over the span of 6 months or so.
No.
Not even. No.
Well,
Yeah,
I guess
it's about that. Yeah.
Yeah.
Yeah. So they all handle the rest of this.
Sorry, Miranda stole my mic. All right, so we'll start with the most important part, the part that holds it all together, the frame. So this is my joy. So you can see we have these fancy looking arrow pointed looking metal extrusion bars. They're called 80-20 extrusions, and they're really cool because if you kind of look in the picture, you can see the fasteners there just like slide into that T slot, and they're really handy. And they are, as I have noted on the slide, they're both modular and adjustable, which means that we can like move them around and like things slide really nicely, and they're very strong, and they also look really cool. So that is what we have chosen for our frame. It looks pretty good. And I guess you go to the next slide. Another similar thing is the bearing support. So you can see there's like a metal plate which is bolted to the extrusion bars, and the flywheel bearings rest on that plate. And I have a note on here about manufacturability, and that is something that I think is noteworthy for these like very, it's you have like a project, and like you're thinking about the flywheel, you're thinking about the motor and all that stuff, but then you also have to think about how we're actually going to put it together, and how is it going to hold itself together, and am I going to be able to screw that in, or is it like in a corner that I can't reach? And those are important questions, and those are some questions that we answered with our design. So that was what I did.
And next we have Ivan to talk about the axle and flywheel simulations.
Hello, everybody. So for my part of the project, I did a lot of finite element analysis on SolidWorks. And so basically what we're trying to do here is to make sure that the flywheel would not explode or come off the bearings and do something that's potentially very dangerous. And so in order to make sure absolutely nothing disastrous would happen, we put in some very exaggerated test conditions. So like make a really, really much more heavier flywheel and give it a big imbalance, and then run it at an RPM that's higher than we probably will. And then we put it through motion simulations on SolidWorks to test for the vertical reaction force. And that's mainly to make sure that the bearings will hold, as well as put it through a static test to make sure factor of safety holds up. And that's more for the axle. So with these tests, we were able to make determinations for what bearings we're going to use. Oh, Juan, next slide. Gracias. Yeah, so basically we ultimately decided on McMaster parts for mounted ball bearings, which are easier to mount. Wow, hence the name. And D-shaft collars, because we're actually using a D-shaft axle in order to enable the flywheel to spin with the axle itself. And then beyond that, we also I focus on the Drumwheel, which is another alternative form for us to kind of like connect the engine to the flywheel without necessarily taking the engine out of the vehicle. And so in this case, we just use the drive wheel to run on top of what is essentially like a storage drum. And then that is connected with chains to the flywheel. And that's another way for us to be able to measure efficiency without necessarily as much hassle. Yeah.
Next, let's have Sophie talk about the bomb.
Yeah, so the BOM is what we call the bill of materials, which is every part that's included in the dyno assembly. Actually, the electronics hasn't been added, so I'm sorry about that, but important part. So it starts out in SolidWorks. On the left side, you see the file tree, and everything's organized into folders for every like portion. And then in SolidWorks, we can expand this into a table. So you get like a cut list of all the like metal bars and lengths and stuff. And then we just reorganize it into a nice spreadsheet with links and quantities, and it's very neat. So that makes it more readable. A lot of work goes into it. And this is for the gears and chains of the dyno. This is how this is really important to measuring the output of the engine. So the teeth, if you look, it's pretty straightforward. The teeth is the number of like pokey things on the gear. And ideally we want both gears to have the same pitch, which is distance between the teeth. So gear ratio is a simple ratio between the number of teeth on each gear, and it determines the speed of rotation of the engine and what is being measured. And we choose pitch based on what kind of torque we operate at. So for the panels, this is kind of an extra feature, but we think they're pretty cool because they not only contained all the parts inside the assembly and made sure no parts flew off. Polycarb is a good choice because you can like see through them pretty clearly, so you don't have to keep opening all the doors and stuff. They have a really good strength to weight ratio, so it wouldn't be too hard to install or use. And we got them for free from one of our very cool partner companies.
Wonderful. Now we'll have Jake talk about the latches and hinges.
Hello. As you can see, the dyno is beautiful, but if we can't get past the polycarbonate panels, it's useless to us. So we wanted a way to easily access the inside, the flywheel. And so we decided on allowing two polycarbonate panels to open outwards. And so we, courtesy of 80/20, we went with 4 different panel hinges that allow us to open it. And then while the flywheel is running, we expect vibration. So we are using slide latches that just secure the panels in place along the main frame. And we also have 2 magnetic latches that keep the panels flush against the frame as to prevent any movement, and that will, yeah, any unexpected movement.
Next, we have Jinkai on electric braking. Is Jinkai on the call? If not, I can take it.
I don't think he's on. You might want to take it.
Okay. Yeah. So for electric braking, what we want to simulate is the friction that you get from both air resistance and friction from the ground. And how we do that is by basically using an electromagnet to put it close to the flywheel. And by changing the current that we feed to these magnets and basically the power that we put through them, we change how much force we put to brake the wheels. And there are several reasons why we want to do this. Basically, to make it more efficient, to change how much strength we want to put on, how much drag we want to put onto it. And also it allows us to do some simulations as well, which Jinkai worked on, and he might be able to answer better, and basically simulate what's going to be the effects of the flywheel spinning at different RPMs. And this is a little render as well of the magnetic discs. And this is sort of something that might need some more work, but at this point, it's basically a bunch of magnets put together that we would wire together and control them with the electronic sides that you'll hear about a little later. And then we have some statistics here. For example, we have the 400 kilogram force electromagnets, and they can withstand the force and torque of the different of the flywheel spinning, right? And we have also the fact that they bring eddy current by being close to the flywheel. You can also see right here, we have a little latch. The idea there is to connect basically a spring or a, forgot the other term, but a spring basically to measure how much it turns by. Come again?
Strain gauge.
A strain gauge, correct, yeah. And that way we can see how much torque by using the radius and how much deflection there was. Next, we'll have Ash talking about the dyno control panel.
Yeah, absolutely. So thanks, guys. We've established the mechanical side of things so far, but now we need a mechanism to control all of that information and actually collect the data out of the output, which is one of the most crucial parts. So I had a lot of fun creating this little dashboard using Python. There's a UI library built into Python called tkinter, which is what I use to create this framework. And as you can see on sort of the left-hand column, you have all of the different data values like current voltage, RPM, temperature, et cetera. These are being read directly from sensors that are placed around the dynamometer. And then on the right side, you have sort of the control aspect. You can change the strength of any magnet, any of the 8 magnets by inputting a number from 0 to 10. And you can change the throttle response, the throttle input to the motor or the engine via this little slide bar. And you press push and it sends all of that data to the actual dynamometer. And the beauty of this sort of panel is that the data is really accurate because it's reading in real time via Python. It's extensible, so all of the code was written to be able to add new sensors very easily, take out old sensors, change the number of magnets. All of these different parameters are highly tweakable, sort of designed to make it fun as well. So I had some, I'm not a designer, but I had some fun putting this together in Figma. So yeah, that's it.
I don't know if I cut Marcus off if he was going to say something.
Oh yeah, I was gonna comment on the magnet wheel. I just wanted to say that it's really important because the car as we're driving it is experiencing forces that slow it down, and we can model those with because the magnets are adjustable for the strength. We can model those forces the car experiences with the magnets, and so it allows us to do really, really detailed testing for like simulations of actual driving. So I just want to put that out there because it's definitely a really cool thing about that.
Thank you, Marcus.
Yeah, and then sort of the next step after you've inputted your information into the Python dashboard, that gets sent along a signal, along a wire to their microcontrollers, which actually interface with the sensors and control the throttle. So in order to sort of handle that communication, Abs and I worked out a clever little communication protocol to standardize the messages. We've also created sort of an acknowledgement so that we know for sure our commands get received by the microcontrollers. It's designed for efficiency all the way around. uses, again, the modular design so we can add or remove sensors whenever we want. And all of the documentation is clearly written on GitHub so that anybody can check out our code and understand it relatively easily. We spent a lot of time setting up our GitHub peer review system to facilitate this. Yeah.
Awesome. Let's have Abs go a bit deeper into the electronics.
Sure, yeah, just to build a little bit more on what Ash was just talking about, I work more on the other side of that communication link on the microcontrollers. Yeah, and also just to touch on what Marcus was talking about with the adjustable magnets. We laid a lot of very solid groundwork in terms of being able to you know, expand the number of magnets on running on the dyno, you know, running them at pre-adjusted strengths, adjusting those strengths, and also we do have a pretty solid base to then eventually, and just talking down the line, being able to run preset, almost like templates for how, you know, kind of simulation runs that, you know, if we can go out and measure the forces that are exerted on our car, we can then go back and, you know, almost pass that to our dyno, tell it, okay, we want to simulate this run with some tweaks we made to our chain drive system, and let's see what happens there. So a lot of solid work being laid there. Gonna take a little bit of a higher level view here, talk a bit about the architecture and how we laid it out. As you can see on the left, the Latte Panda is kind of the new brains that we've installed in our car. So the fact that we have the DAC implemented on there, the dyno, and we're also moving compatibility from motor control to be able to at least run through the Latte Panda, you get a lot of features for free. You get the fact that, you know, now these key systems can interface and talk together. So you can now think of, you know, this whole system as a suite. So ideally, when we're running our dyno, you know, like Ash was touching on with the throttle, all these three systems are running together. It's all under one system, and it's all integrated under one dashboard, which is a super powerful thing, as opposed to having each system run independently of the other. On the right, you can see this kind of you know, component schematic for essentially everything related to the dyno. On the top right is power distribution. That's the battery and the relay. You can think of the relay as like this electromechanical switch to turn the car on. Kind of to the middle right of the schematic, you see the magnet and a MOSFET. That's related to what Marcus was talking about kind of modulating the signal to the magnet. We actually have 8 times the MOSFETs and magnets. This is just kind of a high level view of the schematic. And we have the Raspberry Pi and the microcontroller on the bottom. Again, we use a Latte Panda, which is essentially a more spec'd out version of the Raspberry Pi. And then we have a Hall sensor to measure RPM and a potentiometer to use as a handheld throttle if we wanted to as well. Next slide, please. Cool, yeah. Not the most beautiful schematic in PCB, but we did manage to get most of that schematic on the previous slide onto our PCB. Power distribution aside, we typically do that outside of the case or outside of the PCB. But yeah, the goal is to be able to essentially have everything on this one PCB. And then again, we have a PCB for our DAC system or dual meter, and another PCB for motor control, all connecting to the same Latte Panda. And then, you know, again, I can't stress enough how powerful that is to be able to control all three systems from essentially one hub. Yeah, that's kind of my bit.
Awesome, thank you. And before we open it up to questions, that was pretty much all of it. And the idea here is, you know, this is some motivation of what we did over the summer, what we've been working on, and it's really open. You know, SMV welcomes all of you guys and whoever wants to make things. If you want to go build something, go do it, get a team together, and we'll make it happen. If anyone has any questions, feel free to shout them out or anything. We've got Jeff asking, how will you accurately balance the flywheel? That's a good question. Ivan, might you want to take that one?
I think so. So our plan is to get cast, like we get steel and to get it cut with water jets, I believe. So inevitably like there will be some imbalances perhaps when I'm cutting it. Ideally, it's not going to be as bad as having a massive hole on one side of the flywheel. So that's kind of like the whole purpose of the simulations, is to understand that, oh, there's going to be some imbalances in the flywheel, but like, so we're just going to exaggerate that to a very extreme degree and make sure that it won't make the flywheel malfunction. Yeah.
There are there are techniques specific to like aircraft and like propellers where there are methods to balance a propeller, and it usually consists of putting it on like a dedicated stand and having it like rotate itself to indicate that it's off on one side or the other. So you might investigate that sort of method to get a more accurate like sub 100 gram imbalance in the flywheel.
Yeah, for sure.
Awesome. And we have a question from Isabel. Does this working with the engine rely on GV having electronic throttle control?
I can take that one. Yeah, on the dyno control panel, there was a kind of window for the throttle. Again, that's mostly an EV motor control integration. That doesn't mean that obviously the dyno doesn't work with the GV motor. All that means is that you'd have to actuate the GV engine, separately to that. Again, that's not to say it can't be integrated in the future, but that's just not something that was baked into the design to begin with. Does that kind of answer the question? Ash,
Yeah, it
anything
does. Thank you.
to add to that?
Yeah.
Cool.
Yeah, I think I'll add at a higher level. The project was designed for both an electric motor and a gas engine in the same sort of system. And that produces a lot of interesting challenges because the form factor of a motor and an engine aren't really the same. The way we mount them isn't really the same. The way we control them electronically isn't really the same. So there's a lot of sort of layers of abstraction that we've implemented to make sure that what is common is as common as possible. As Abs mentioned, sort of having one central port where you can control all of these different systems is yeah, that was a huge motivating factor in a lot of these design decisions.
With a flywheel, it can be balanced, as accurately as you can. But with the engine mounted inside, you have this inherent vibration due to like the reciprocating mass inside the engine. So has there been any significant thoughts on reducing the potential for fasteners to become loose under vibration and other safety hazards?
I think Jake might want to talk a little bit about that with the bolt preloading.
Yeah, so for the bolts we are using, they all have a certain preload that we will tension them to, and we have a torque wrench in the shop which will allow us to accurately preload each bolt. And if we do this correctly, this bolt preload should ensure that the external vibrations won't allow the bolts to come loose. But I definitely need to do more research into that, because that was one of the last things that we worked on. But overall, from my research, it seems like we have a good understanding of what needs to be done when we are actually constructing the dyno.
At the same time, we did meet with an alumnus from UCLA who worked on SMV previously and worked before in SpaceX. And he told us a little bit about that as well. He mentioned that sort of trying to do the calculations on whether vibrations would affect our design. I forgot how the saying goes, but like using something huge to strike a tiny thing, like a tiny nail or something. Basically, it's like overkill, doing it way too hard. He said with the design that we currently have, we should be good enough with the bolt preloads.
Yeah.
Now we have another question. First, we have Ash. What are the next steps for this project? That's a great question. Well, I think the solid first step is making it happen. Like looks pretty, but that's a render. That's not the real thing. It would be awesome to be able to build it. Of course, given the situation, we might want to push that later. But I think that's the biggest thing first. I think moving forwards from that, I think more it's less tested and see what we can improve, right? Put the car, do some tests, test it on the different ways by taking out the engine or by doing it directly with Ivan's Drumwheel, and decide from there, what can we improve? However, one of the things that we might want to look more into as well is the magnetic wheel, because there's a lot of difficulties that we had with basically making that manufacturable, stay standing where it is, and not conflict with the flywheel. If anyone else has any other thoughts, please feel free to jump in.
There's a question from Arnon in the chat.
All right. Arnon or Heeson? Was a structural simulation done for the entire dyno with the pillow blocks attached to the frame, etc.? No, we have not done a structural simulation with everything together. But we did start considering sort of the important areas. So for example, for the weight of the flywheel and everything being balanced in the middle, we decided to look, simple 101 beam bending. If we take a look at this beam and we take a look at this weight, what's going to be the deflection? Or is it something that we have to worry about shear stress or anything like that? And that's actually one of the reasons why we put little support beams right here, because instead of worrying too much, we decided to go further and put an extra beam there.
Does this design require significantly more tooling to be bought by SMV to manufacture this? And do we have room for it?
That two-part question, I don't know if Sophie might want to answer part of that, and Ash talk about how much money we got.
Ash, you're muted.
I'll let Abs handle the money.
Sure, yeah. I can talk a little bit to that. As far as I understand it, a lot of the dyno, has been designed with an eye towards being able to, bring in the materials and manufacture it ourselves. I can talk a bit more on the finances side. We have been compiling our budgets. The dyno is 100% a project that we've had in mind when compiling those budgets, and I don't think there's a fear that there's too much tooling that we have to buy in order to manufacture this. And it's my understanding that there aren't any huge tooling expenses. Anyone is free to correct me if I'm wrong. I'm not too sure about that, but yeah.
Yeah, that's pretty much it. I think the other thing is that it would take us more time to figure out how to do it rather than have some of the manufacturers who sell these items do it for us. For example, I know we discussed this a little bit. These little parts to attach them, right? You see this circle? It actually has to be machined out in order to put it in. And that's something that you can tell the manufacturers to do. Imagine trying to ourselves get holes in those and all the ends. Forget about the precision, just trying to do it would be really difficult.
I can make another comment about the future steps for the project.
Go for it.
Yeah, so something that we've been thinking about as like the next big step, I guess, like besides finalizing design and assembling and all those things, is actually the experiments that we're going to be running on the dyno. So I've been working with Min and Ash, and we've been talking about how we can create code that has like recipes. So we can create a recipe that says, you know, control the voltage to this level and measure the acceleration and blah blah blah, and we can have that as a recipe and have the system run it all automatically and give us the results. So we're designing experiments to, like, in that format to run on the dyno that we'll have it ready, have the experiments ready by the time it's built. And we're also looking into running simulations of actual driving. So like, yeah, like actual driving, like not even like actually having like the course and like the turns and all those things. Those are in the future plans. That's some exciting stuff.
Yeah, for sure. You mean like comparing the car actually driving on the road versus this, right?
Yeah, actually simulating like every turn and every hill and the speed with the air drag and all those things. Those are in the works.
There's going to be a lot of sensors in this system, as well as high power components. Have you thought about ways to prevent your wires and other dangly bits from getting into rotating elements in this system?
That's a good one. Ash or Abs?
Abs?
Sure, I'll take this one. Sorry. Yeah. Mounting electronics is something that we've touched on. Well, not in the presentation, obviously. It's a very valid concern. I think, as far as I'm aware, the current plan is to essentially house the PCB in one of the corners of the dyno. As far as making sure wiring doesn't get into any of the rotating bits, the primary concern is the wiring that feeds into the magnets. Not so much the other wiring, so long as obviously everything is tied down well, our wiring harnesses are solid and all that. So yeah, the main concern is, again, just the wiring connecting the magnets. And yeah, I mean, there haven't been any sort of like major considerations as to how to avoid that, as opposed to just, you know, just keeping in mind those main obvious design considerations.
Yeah. At the same time, talking about like the physical layout, I couldn't find a better picture, but the thing that you're worried about is this guy spinning and this guy spinning. And where the wires are really focused on is right behind here, where this is the magnetic wheel. So most of the wiring is going to be behind this big wheel. So it's going to be protected anyways. But the important point is just not having any loose wires, really.
And
I just want to stress again.
T-slot is like inherently hollow too. So you can do some creative things where you can put wires inside of the T-slot, and it's like neat and yummy. Yeah.
Yummy with the recipes Marcus is talking about. Looking good.
Just for everyone on the call, the flywheel is separate to where the magnets are mounted. The magnets are mounted opposite to the flywheel on a static mount, I guess, to just apply the braking force. So there's no fear of the magnets spinning and having the wires powering those get tangled or anything.
Yeah, sort of to make it easier to see, this steelish, more steelish colored is the one that spins. The one on the left doesn't spin at all. It just slightly turns if there's a lot of torque on it.
With the large electromagnets, are you using a direct current or alternating current to drive them?
That's a good question.
Could you repeat that?
Are you using a direct current or alternating current to drive the electromagnets?
No, they're just DC current. If you go back to the schematic real quick, Juan. Cool, thanks. Yeah, we've got a FET with a magnet. if we ever needed to kind of simulate alternating current, an H-bridge is something we could swap the FET out for. Yeah.
I think someone else. I think I spoke over someone.
But yeah, are there plans to like make it mobile so like we can, especially with the GV engine, right? We have fuse and stuff like that, so it can't run in the shop at all. Yeah.
Yeah, great question. I don't know if it's in the bomb picture, but yes, there's some simple wheels that basically we can attach right at the bottom. I don't know what I'm looking for, but we can attach them right at the bottom, and it'll basically allow you to lock it in place once you want to use it. And they're like sturdy wheels that are worth the money in order to make it stable. So you lock them in place, not those cheap ones that don't lock, the ones that like really lock, and then we can use them wherever we want. Yeah. And actually, now that you mentioned that, the other idea was to, in order to make it compatible with where we currently rest the cars, we can lower or raise the height of the, what they call it, the car stands, in order to make the wheel just nice, hit the drum, to spin it directly without having to place it or make another thing. So we can directly use what we have already.
Okay, cool, nice. And then I guess also like since it's mobile as well, how are you gonna power it again? I think I might have missed that.
Very similarly to how we currently power the EV, a battery with a proper case for it, or battery mount, a relay, and I guess a shut off and all that kind of thing. Does that make sense?
Yeah, it makes sense. I see. Cool. Do you know like how long, like how big of a battery you need, and like how long it'll be able to run for and things like that?
Good question. We actually haven't spec'd out the batteries just yet, but I guess the running assumption was that we would use a similar battery to what we use with the current EV, because presumably the battery running the whole system would also be running the motor control system. So with our current car, the battery that we have, or the 36 volt battery that we have, is enough to finish a complete course around the typical track at Sonoma. The 24 volt battery has higher capacity, so there isn't any fear of running the system and running out of power for like a run that's at least as long as the official runs. And for GV, that would obviously go longer because you don't have an electric motor to run.
Okay, cool. I see. I think if like you guys need high current as well, I think like even like a car battery will work in this case. I mean, like it's giant, but it might be helpful to use for just the dynamometer, since it's not really, doesn't need to be mobile, right? But yeah.
It's true.
Nearly all industrial machinery contains interlocks to prevent operators from moving into unsafe situations. So has there been any thoughts on including interlocks, like panel interlocks and things like that, to prevent any operator from having their hands inside the machine while it's on?
I can't exactly answer that, but I can say that we have, for the same thing I was talking about earlier, the thing that runs the experiments, we've looked into having like kill scenarios. So for example, if the temperature sensors read too high of a temperature, it'll auto shut off. If the RPM is stuck really low for too long, like say 2 seconds, it'll stop because that would imply that it's stuck. Or alternatively, if it's too high, it'll auto turn off. So we have looked into things that would trigger it to shut down automatically in terms of like software. Yeah, I don't know about the mechanics.
I would suggest panel micro switches, which you can buy. I think you can definitely buy them for 80/20 extrusion, because that's a very common industrial machinery thing. And you can buy micro switches that are specifically designed for panels on top of 80/20 extrusion that you might hook into your system.
Yeah,
So then we'd be able to load, like if it opens up, if anyone opens it and like kill it.
Yeah, exactly.
We're sort of running out of time. Maybe if there are any new members that have any questions, we'll open it up to them.
A question.
Yeah.
Back on the topic of power sources, have you looked into the power source being a limiting factor at all? For example, if you're running, just considering the EV motor, if you're running even a few kilowatt motor at anywhere close to max power plus very powerful electromagnets taking like almost 100 amps of current, it said in the chart, I would think that a battery would sag in voltage quite a bit and wouldn't be able to drive the entire system at once, supplying how much power each of the devices needs.
Cool. Yeah, thanks for the awesome question. Yeah, these are all considerations we actually actively tackle on EV powertrain side, especially when we think about building our motor controller, because these are all considerations that are 100% still valid when we run our car without a dyno. So obviously the most straightforward way that we do this is by putting these relatively massive bulk capacitors on our motor controller. Those help with mitigating that sag. Essentially, those capacitors act as like a bank for that power to supply when the battery starts to sag. Otherwise, yeah, our motors are relatively lower power. The highest motor power we had was, I think, 1,000 watts back when we ran a brushed motor our first year. Right now, I think we're sub 500 watts. And we haven't had too many issues with just running a 36-volt battery with, I think, 5,000 milliamp hours. So yeah, power is a huge, very important consideration. Thanks for bringing that up. But yeah, I guess we've just kind of, at least under the dyno context, just assumed that we've covered that from EV powertrain.
To add on to that, worst case scenario, we can use it with plugs, right? Like, for example, on the top of like the parking structure where we test it, we can hook it up to some power, right? Like wall outlet.
That's a bit more complicated. We could probably do some sort of DC to DC conversions and get that, but yeah,
it'd be easier just to get it with the.
Yeah, again, we want to go back to that idea of running the whole system from a single source, right? And it's just easier to do it with an out-of-box battery that just runs the whole system. With that, I just want to say real quick, we are running out of time. For those of you who are involved with composites training, that starts in 4 minutes. So I don't want to keep us going for too much longer so that you guys can take a breather between now and then. But yeah, we'll still hang around. New members, if you have any more questions, feel free to shoot them at us as well. Yeah.
Sure. Okay. One last question. With a sort of an isolated system, especially one on wheels, and one that contains a large amount of power electronics, there becomes an issue where you don't have a secure path to ground at all times, and that presents a safety issue to operators, where potentially the chassis may rise to a high potential, and the operator becomes the path to ground. Has there been what is your strategy to prevent the chassis from rising to a high potential or presenting an electrical shock hazard to the operator?
That's a good question. That's not a consideration, honestly, that we've had. Yeah, definitely something we should look into. Anyone else have any other comments to?
Is that a concern in our car? No, right?
So in our car, we have a common ground throughout the chassis, but again, it's a moving vehicle, right? So it's not like we ground it to earth ground.
Yeah. it might be something that you take like an isolationist strategy and like protect as much as possible from it ever touching the chassis instead of the chassis. I'm not an electrical engineer, but that was just a concern that I had.
For sure.
Seems like it's about time to wrap it up. Thanks again for everyone for listening in and all the questions. Really appreciate it, and I hope you guys enjoyed. Can't wait to see what you all cook up next.
Thank you, guys.
Cheers.
Thank you.
Thanks, everyone.
Hey.
Sorry for that really bad question at the end.
Jesus, man.
Wait, it's still recording. Still recording.
Oh, oops.